All right, parametric equations. Well, the nice thing about these is that they always go by the same name. Everyone always says parametric equations, and the whole deal is just converting between parametric equations and non-parametric or rectangular equations. So here's a couple of examples of parametric equations. The big deal is they come in pairs of equations. There'll be two equations, and this will actually graph on the xy plane. So you'll notice we have three variables here. We have the usual x and y in each one of these pairs of equations, but then we have another variable, usually t, but sometimes theta, if angles are involved. If trig functions are involved, they usually call it theta. But the point is that's just an extra letter that's kind of like there for no reason. It turns out that if you wanted to, you could take any parametric pair of formulas and convert them to a regular xy equation, or you could take a regular xy equation and convert it to parametric equations. And we'll do that in the next couple of videos. In this one, I just want to talk about what parametric equations are, why you shouldn't be afraid of them, and show you how to graph them. Because there's one subtlety to the graph, which is that there's actually a directionality to it. So now if you have the parametric equations of a circle, like this one on the right, it's not just a circle, it's a circle with a direction to it. Because as theta gets bigger, are you going this way or are you going this way? Tough call. We'll talk about that in the last video in this chapter about parametric equations of conic sections like circles and ellipses and stuff. But the point is now, and that's where we'll talk about how to recognize the equations of circles, sine and cosine, stuff like that, what they mean. But for now, let's just talk about in general what parametric equations are and how to graph them. So it turns out the big trick is to just plug and chug. So you might be thinking, hey, but normally if you wanted to graph a function of x, you would pick an x, plug in a y, pick a different x, plug in a y. You get a bunch of points, right? So you get like 1, 1 and 2, 3 or whatever. You just pick one, you pick x's to get y's. Well, in this case, if we picked an x, we can't plug it in anywhere, right? The only thing we can plug here is a t. So instead of picking values of x, we're going to pick values of t and plug them in. So you can make a t chart if you want, like t and x and y or something. But the point is that to get an idea of what the thing looks like, your options are convert the parametric equations to a rectangular equation, and which you might recognize. Like this one has a squared in it, so I'm pretty suspicious it's a parabola, but we'll see what happens. Let's try plugging in 0 for t. Then we get 1 for x, and we get 0 for y. All right, so the point 1, 0 is on the graph. Let's try plugging in 1 for t. 1 plus 1 is 2, and 1 squared is 1. So we got the point 2, 1. Now you'll notice that the value of t is not on the graph. So that's kind of the confusing thing. T was just a number we're plugging in to get the two numbers that are actually coordinates. But now you'll notice, and if we plug in, I'll plug in -1 as the last one, so we'll definitely see what we're looking at here. Plug in -1, you get -1 plus 1 is 0. And plug in -1 squared to get +1. All right, so we got point 0, 1 as well. All right, so what graph do you think we're looking at here? Looks like a parabola, right? So as expected, that t squared, the fact that we have a squared t in one of our equations and no squared t in the other one did in fact lead to a parabola, just like you'd think with a quadratic or something. But check this out. Now the one thing we left off, and I kind of blew it by putting these arrows on the end, is that these parametrics have a direction. So the question is, as t increases from -1 to 0 to 1, what direction are we moving along the path? Sometimes they call this graph of parametric equations the path. And as we went from 0 to 1, we went from x is 1 to x is 2, so we're moving to the right, and we're moving y bigger. So we are going this way along the curve. So the direction of this parametric path is along from upper left, swooping down through the vertex, and then up to the right. So if we started plugging in bigger and bigger negative values of t, we'd be going backwards against the current here. But then as your t gets bigger, you go with the arrows. So the reason they call this a path is because that's the one thing that parametric equations are actually good for, is talking about the time it takes for something to move along a path. So for example, everyone knows that if you kick a football or throw a rock or whatever, in Earth gravity, the path is going to be an upside down parabola. Just projectiles flying through the air go in a parabola. But the problem is that if you give that parabola in terms of x and y, like, I don't know, y equals 300 minus x, 4x squared or whatever it is, for this particular parabola, that doesn't contain any information about how long it takes for the projectile to go along this path. All it's saying is, hey, if you sort of traced out the path, it would eventually go through this parabola, but every parabola kind of looks the same. You don't know if it took a long time to go through this arc, a short period of time. So that's what's really great about, and you get this in the projectile motion chapter, but if you look at the equations of projectile motion, they are x equals v0 in the x direction, t, and y equals, y is 0 plus v0 xt plus 1/2 at squared. So what do those look like to you? Don't they just look like a couple of parametric equations? I have x as a function of t, and I have y as a function of t. So that means that any time you plug in, you'll get the distance. All right, so here's another one we can plug and chug through. Now this time we got theta, some trig functions, but otherwise it's just the same. We're just going to plug in different thetas, and we'll get x's and y's out of that. So let's try plugging in 0. Then we get the sine of 0 is 0, cosine of 0 is 1. Try plugging in pi over 4. Then we'll get root 2 over 2, and root 2 over 2. Pi over 2 gets 0 and 1. And you can kind of see how this is going to go. It turns out this happens to be the parametric equations for the unit circle. That is a circle of radius 1 centered at the origin. So as we just go around this puppy, we're just going to keep going around and around. And since there's no limit on theta, like it didn't tell us, hey, theta is only between 0 and pi or something, we're just going to keep going around and around, and we're going in the positive direction. So that is the direction of the path. So we're going around a circle, and as theta gets bigger, we're going to be going counterclockwise, the same direction you would for the unit circle as angles get bigger. Pretty exciting stuff. Now, the arrow is something, if you leave it off on the test, your teacher might have a conniption and take off some points. So just keep that in mind, and if you have one of those teachers who likes the arrow a lot, and specifically if it asks for the direction of the curve, or the direction of the path, then definitely put the little arrowheads on there. All right, here we got what I was saying a second ago, projectile motion. Pretty good example of parametric equations. Now we're going to have, it's not up now, but soon there will be a chapter up on projectile motion on this website. But for now, let's just take a look at a quick parametric example of projectiles. So as I mentioned, a parametric pair of equations will tell you the x and y coordinate of a projectile as a function of time. So this t right here, that literally just means seconds. And pretty much always that just means seconds after the throw or gun goes off or whatever it is. So whenever you look at a projectile problem, you're looking at something that was either thrown or shot out of a cannon or a ball that was kicked. Whatever the deal is, a projectile suddenly got launched, right? So that's when time is 0, is that moment of impact, that moment of launch. And then time from then on is just you plug in however many seconds it's been since the object was launched. So in this case, you'll notice there's a lot of detail in this equation, in this problem, but I'm giving you the equations of motion. So normally these physics problems and projectile problems, part of the hard part is reading through the problem and trying to figure out what to plug into the equation just to come up with this pair of equations. You know, figure out the initial velocity, the acceleration, blah, blah, blah. However, a lot of times in these parametric chapters, they'll just give you the equations, and they'll word it like this. They'll say, hey, this happened. You know, these numbers are relevant because they're already in the equation. And then they'll ask you the projectile's position, and they'll give you some times to plug in. So 0, 2, and 10 seconds. So let's just try plugging them in. So when t equals 0, let's just do our usual chart here with x and y and stuff. So when t equals 0, you plug into the x equation and you just get 0. And you plug in 0 to the y equation and you get 50. And it turns out that makes a lot of sense because we're throwing this object from the top of a 50-meter high cliff. So it makes sense that when t equals 0, i.e. the instant the thing is thrown, it's still right there at the top of the cliff. So our y coordinate is 50, you know, assuming that and you can actually tell by looking at this equation, they're saying that the initial y coordinate is 50. But they're, you know, as is often the case with these projectile problems, the origin, the coordinate system we're using here, is based at the ground level. So here's a 50-meter cliff, and the object's being thrown off of here. So it's going to follow an arc like that and hit the ground way down here. but the y-coordinate is the height off the ground, apparently, since this 50 is here, not the height from the initial launch. Anyway, so if we want to get after 2 seconds, just plug in 2 for t. 2 times 10 is 20. Makes sense if it's going 10 meters per second, times time, then if after 2 seconds it'll be at 20 meters. And then we'll have to plug in 2 down here, which gives us 70. So that kind of makes sense after 2 seconds that we're, let's see, so our coordinates there, we've gone 20 meters to the right, and we're still 70 meters off the ground. In fact, we're actually higher up than when it was first thrown. So right now we're at 20,70, which is somewhere up here. We don't know if it's before or after the peak. It's a little bit harder of a problem. We'd have to use the projectile, more tricky projectile stuff to figure that out. But the point is, you can tell just by plugging in the amount of time that we're actually right now higher up than when the thing was thrown. So this thing is still somewhere above the thrower. Not sure if it's still on the way up or on the way down already, but it's somewhere up here in the portion of the curve that's above the launch point. And then finally, they ask for what happens at 10 seconds. Well, let's see, we plug in 10 seconds, we get 10 times 10, we've gone 100 meters sideways to the right, and then we've gone 50 plus 200, so 250 minus, minus like 500 for a y-coordinate of negative 250. Now, does that make any sense? Could that be right? Yeah, it could, because this equation, well, in one sense it's right, in one sense it's wrong. It's right because this is the equation of a parabola, and this parabola doesn't know that there's a ground there. So it doesn't realize that, hey, it can't just keep falling forever because it'll smash into the ground. So the truth is that where this rock or this projectile would like to be, this ball, if it had its way, it would be 250 meters below the bottom of the cliff right now. But of course, it didn't make it that far. It crashed into the ground right here. And there was a splat, or maybe the ball popped. That's a pretty tall cliff to throw a ball off of. Who knows what happened? But the point is that this thing hit the ground. So somewhere between 2 seconds and 10 seconds after the throw, this ball crashed in the ground pretty hard. Maybe it bounced, whatever. But this equation, it's not smart enough to figure out whether it hit something or whatever. All it knows is, in an ideal world, with just that parabola and nothing else to worry about, where would things be at any given moment? All right, so that's how you solve, or that's how you plug and chug, I should say, through a parametric equation problem. Now, in the next couple of videos, we'll get into how to switch between parametric and rectangular. And then the last one, we'll do a hard topic, which isn't even in most classes, or some classes anyway, which is parametric equations of conics, like ellipses, circles, and if you're really unlucky, hyperbolas. So get ready for that and avoid it if you can. See you in the next video.